Juneja, Anand is right here. Some of you may know him. In case you have any questions, you can ask him or me. Hari is right here. They will also be the organizers. If you have any questions, feel free to ask us. The buses that come from both IIT as well as from HBCS, is that right? From IIT as well. Okay. Mostly. Alright. It's a first like so I'll tell you the announcement that we go along. There's no major announcements. All the information is already here in the booklet that you have. We have one talk. This is our Narasimhan lecture given by Po-Ling Loh, and that will be in the auditorium. All the other talks for the whole conference are going to be in this room. This is one lecture of 4-5 p.m. that will walk down there. Lunch is also towards the auditorium, towards the foyer. So we'll point you to let you go there. Otherwise, I now request to restart. I was able to introduce Po-Ling and then we take off from there.
Right. Well, thank you, Sandeep and Hari and all the TFS personnel who have helped put this conference together. Thank you, Po-Ling and other speakers for coming. So we're going to start with the short course by Po-Ling on the theory of local optima of non-convex high-dimensional M-estimator. Before I hand over the floor, just a few words about her. She's currently a professor at the University of Wisconsin-Madison. Before that, she was briefly at UPenn. She got her PhD from Berkeley in statistics. She's done some fantastic work at the interface of statistics and optimization. She's got many awards, including the NIPS Best Paper Award.
Okay, thanks very much, Devarat. Thanks, Sandeep, and the rest of the organizers. So I'm going to be talking about some work that I've been doing for the last 10 years. And about half of it is based on work that I did during my PhD. And then the other half will be some more recent things. Oh, wrong clicker. 2 clickers. Okay, here we go. Right, okay. So this talk will be in 2 parts, and there will be a break in between, but I have a feeling the first half of it will take longer than the first half, so we'll just break after an hour, 15 minutes. So the first part will be some background, some research that I did during my PhD on the theory of local optima for non-convex regularized M-estimators. And then after that, I'll move on to some more recent work that I've been doing in the last 5 years or so on high-dimensional robust regression. Okay, so let's start with non-convex M-estimators. So the setup here is that we have these pairs xi, yi, and they're related via an unknown parameter vector beta star that's p-dimensional. And we want to estimate beta star based on n IID observations. And what we'll be looking at is a so-called M-estimator. So an M stands for minimize or maximize, and we want to, in this case, minimize a loss function, which is the empirical average of the loss function evaluated at beta for each of these observations xi, yi. Okay, so this is what people have been doing in statistics for over 50 years. And what we want to do now is to figure out what we should do in high dimensions. So in particular, when the dimensionality p of the unknown parameter vector beta star is larger than the number of observations n, then sometimes minimizing this quantity might not be a good idea. Okay. So instead of that, we want to minimize a regularized version, so we add a penalty. And the penalty will, in general, be a function of beta, and will also have some kind of regularization parameter lambda, which tells us the strength of the penalty weighing off with the loss. All right, so as a simple motivating example that you may be familiar with, we'll look at the lasso. So this is L1 penalized linear regression. So if we wanted to fit the least squares solution to a linear model, then what we would normally do in low dimensions or in a basic statistics class is that we would want to minimize the sum of the squared errors. So our loss here is the quadratic loss. And then we can just solve explicitly. There's going to be a little bit of truncation here and here. But if you solve this explicitly, you get this x transpose x inverse x transpose y term. Okay. But so the issue is that if you look at high dimensions, then what is this matrix? Well, this is a sum of n rank 1 matrices, because each of these xi's is a column vector of dimension p, and we're looking at p at a vector multiplied by its transpose, so it's rank 1. And if we add up n of them, then the rank of this overall matrix is at most n. Okay, but we have a p by p matrix because we're in a setting where p is much larger than n, and then we can't actually invert this. Okay, so if you actually tried to minimize this function in beta, then what you would find is that if p is larger than n, then actually there's a multiplicity of solutions. So it's no longer just a unique solution that is gotten by plugging in this formula. Okay, so for that reason, we look instead at some kind of penalized version. And this is what we wrote earlier as the rho function, which is a function of beta and also has a regularization parameter lambda. And the lambda is weighing off how strongly we want to penalize. The other thing we do is that we want to assume something about the actual beta star in order for this to make sense. And what we assume is that the true beta star vector is actually sparse. So it's in p dimensions, but instead of p, there's also this underlying dimensionality k, which is the number of components of beta star that are actually non-zero. Okay. And the theory that I'll go through during this talk will tell us that, in fact, the solution beta hat lasso is going to be close to the true beta star in some sense, right? So the penalty is kind of encouraging sparsity and then giving us a good estimate of beta star. Okay, so this problem right here is convex. So there's no problem. This is what people call the lasso. It's convex because we have a quadratic in beta and then we have an L1 norm, and that's all fine. Okay, but the focus of a lot of my research has been on non-convex cases. So why would we want to even look at a non-convex problem? Well, in the second half of the talk, I'll motivate non-convexity from the point of view of robustness, but we're not going to get there quite yet. So the types of non-convexity we'll talk about for the time being are some sort of non-convexity that might arise in the loss or the regularizer for various reasons. And one of them, which I'll focus on for the time being, is to correct some biases when you have errors in your measurements. And the other one is when you have non-convexity in your regularizer, and I'll get to that in a moment. So the very first problem that I looked at, which made me think about this non-convexity, was what is known as errors in variables regression. So errors in variables regression is a setting that people have studied in classical statistics, but usually in a low-dimensional setting. So what you look at is yi equals xi transpose beta star plus epsilon, so it's the same linear model, but instead of observing these xi yi pairs, you observe yi zi pairs. And even in low dimensions, so if you now tried to do an MLE calculation for beta, you would end up with a non-convex problem. So there are already some issues that arise in low dimensions. And people have come up with various methods that they try to use to still estimate beta star. Okay, so this is what we want to do, but also in high dimensions. And one thing that you can see straight off is that if you simply said, let's just fit the, they're right.
Maybe I missed it. The relationship between z's and x.
Oh, yeah, sorry, I didn't say. So the z's are going to be some corrupted version of the x's. And the corruption mechanism I'll put on the next slide. Yeah, so some error. So for now, think about it as an additive error. So you just add some independent additive noise. Okay, so if you just ignored the fact that there was error and you just fit ordinary least squares, then you would end up with some kind of biased solution. All right, so if you wanted to, if you got rid of the penalty for now and you said, well, what does this look like? The ordinary least squares estimator in low dimensions is z transpose z inverse z transpose y. And what you really want is x transpose x inverse x transpose y. Maybe I'll write this on the chalkboard. So I decided to make this a somewhat multimedia-like presentation so that I wouldn't bore you with 2.5 hours of talking. So I will be using the board, but for now, so let's say that if I just did v hat ordinary least squares, then that would be z transpose z inverse z transpose y. Maybe I'll call this v hat prime. Whereas what I would really like is something like v hat OLS, which is x transpose x inverse x transpose y. Right? Okay, so we need to somehow correct this ordinary least squares solution. But of course, this is if it were low dimensions, and instead we're going to do things in high dimensions. Okay, so what was our idea? Well, our idea was basically that we want to replace the quantities that depend on the unknown parameter or the unknown observation x with what we observe. So what we had what we did not observe was some xi, yi pair, and instead we observed some zi, yi pair, right? And the case that we can look at is z is equal to x plus w. So all of the rows of z are the rows of x plus some independent noise matrix. Okay, so if I were just doing things in low dimensions, then one thing you might say is, well, you know, this quantity here, well, this is basically like an estimate of the covariance of x, right? And so this is basically sigma x inverse. And then this thing right here, this is an estimate of the covariance matrix of x and y. Okay, so this will be just a p-dimensional vector. So really, beta star is this p-dimensional matrix inverse multiplied by this p-dimensional vector. And what I observe here, if I were to plug in the wrong thing, is that I would have some sigma z instead, right? Okay, so if I want to replace this by something that will not be biased for sigma x, then what I should do is I should look at my sigma x hat can be sigma z minus, sorry, not sigma z. So I can look at z transpose z over n minus the noise covariance. Okay? So what I want to do, just to repeat this, is I want to come up with something to plug in here that's not sigma z inverse. Okay? Or that an expectation is not sigma z inverse. So I want to use some kind of a correction. And the natural correction you would use in this additive noise case is you would say, well, if I'm calculating a sample covariance of z, but I really want a sample covariance of x, then what I should do is calculate my sample covariance of z and then subtract the covariance of the noise. Okay. And similarly, you can look at what this is. Well, this is an estimate of the sample covariance of z and y. Okay. And if you calculate this covariance, you'll see that in expectation z transpose y is the same as in expectation x transpose y. So I actually don't need to correct this. So what I'm saying is that our estimate we should put in is we should plug in this guy and keep this guy fixed. Okay. So this is exactly what we did, but now in high dimensions. So in high dimensions, what's happening? Well, in high dimensions, we want to look at something like a lasso objective. So we don't explicitly write down the closed form solution for the betas. Instead, we're looking at something like arg min over beta of, what do I want to do here? 1 over 2n times the least squares objective plus, I think I wrote this as rho lambda. Okay, so this is the beta hat OLS that I want to have. Okay, so now what I'm going to do is I'm going to expand this out and figure out what terms require this x, which I don't like. So if I write this as arg min over beta, then I have 1 over 2n times y transpose y minus 2y transpose x beta plus beta transpose x over n beta. And then I still have my regularizer term. Okay. And now I can say, well, the terms that depend on x are this term and this term, right? And so I don't know x. So my naive guess is to plug in z instead, right? So, so the solution, well, let's call this, okay, so the naive solution, which earlier I put as beta prime OLS, is going to be the arg min over beta of y transpose z over n beta, negative of that, plus beta transpose z over n beta plus rho lambda of beta. Okay, so what have I done here? I've just ignored the first term because the first term didn't depend on beta anyway, and I'm just trying to figure out what I need to do to this objective. And then I said, well, I didn't see x, so naively I'm going to plug in z, and I'll do that here and here. Okay, so by our argument earlier, this term should be fine because in expectation it's the same as if I just put in the x. This term is the bad term, so I'm going to replace this. My corrected estimator will make this z transpose z over n minus sigma w. Okay, so that's what I've shown here. So that's what we call, this is capital gamma hat, and this is lowercase gamma hat. Okay, so what I've given you is a nicely motivated way for solving something. So if I said, give me some objective function that I can try to optimize and hopefully it will give me a good estimate, then this is something reasonable. Okay, so then the hard part, of course, is saying that it actually does work. Okay, so here I've rewritten the objective for our case where z is equal to x plus w. You can also imagine cases where z is a multiplicative corruption of x. For instance, if it has missing data, you can just think about every entry of the X matrix as being independently dropped with some probability. And then what you would need is a different kind of correction for both of these terms. Okay. But one thing that you need to note is that a problem with this straight off the bat is that it becomes non-convex. It might not be super obvious at first. So at first you would say, well, what's wrong? I mean, it's still some quadratic in beta, right? And this is an estimate of sigma x. And if I assume that sigma x is a positive definite covariance, what's the problem? Okay, so the problem is that this red term is actually not going to be positive definite. It's not even going to be positive semi-definite. And it's for the same reason that earlier we said that inverting x transpose x is a bad thing to do. Okay, so earlier we said that if I look at this term here, then this is not invertible in high dimensions because it's a sum of n p by p matrices, and p is really large, and I don't want to invert that. And similarly, z transpose z over n, this is a sum of n p by p matrices, so it will have some zero eigenvalues, and then now I'm going to subtract some positive definite matrix. Okay, so that's a problem. But the nice thing which we were able to establish in our theory is that in fact, it's not, even though it's non-convex, it's okay. So the shape of the function is that there are local optima that are not the global optimum, but they're sort of all close together. And so this is one case where if you just run some kind of gradient descent algorithm, then it's still okay. You can pretend it's convex and find a solution, and it will still be well behaved. Yeah. Yeah. Yeah, so there's one thing that we thought about a bit when we first did this work. How do we get around not knowing sigma w? And we never came up with a good answer to that. Because in some sense, like, it would require, if you want to estimate this, I mean, you have to estimate now this giant p by p matrix. So the best we could say is what people sometimes say in the measurement error community, which is that they say, well, okay, I mean, maybe I actually know what the noise of my instrument is. Because you're thinking that you're acquiring these signals and then each one has some noise. So you can see by calibrating your machine just what this noise is. Okay. So that was a reason for looking at non-convex losses, right? Because, I mean, if we just made this regularizer still L1, then that's convex and that's fine, but then the loss is non-convex. But now let's look at a problem, or let's discuss why we might want to look at non-convex losses. Okay, so if we go back to Lasso, where we didn't have to correct for this measurement error, and the loss function was convex, then even then we might want to look at regularizers that are not L1. And what's the reason for that? Well, if we think about this L1 penalty that we put on in the Lasso, that's to encourage sparsity, right? And to encourage sparsity, what you kind of want to do is you want to put a regularizer which is L0. L0 just says count the number of non-zero entries. And the function applied to the beta would just be this, which is that it counts 0 if it's 0, and otherwise it counts 1. Okay, but then in Lasso, what people do is, in order to get a convex solution, they replace it by this L1. And the nice thing is that, in spite of doing that, the Lasso still has good properties. Okay, but actually, it's not quite the best we could do. And in order to do better, what we want to do is we want to come up with some kind of a function that maybe interpolates between these two. So we want it to be convex, hopefully, or at least people did in the past. But then also have a shape that is that gets flatter as you go further away from 0, rather than growing off to infinity. Okay, so there have been various non-convex regularizers that people proposed in the statistics literature, and the most common ones in statistics are called SCAD and MCP, smooth clipped absolute deviation. So that's the green one. So basically, what it looks like is that locally it looks like L1, and then after that it becomes quadratic, and then after that it becomes flat. Okay, so that's this clipped absolute deviation. So clipped absolute deviation would be that it's just absolute value and then it's clipped. But now we're smoothing it. And then there's a related penalty that's called minimum convex penalty, concave penalty, and that's the red one. And the only difference there is that there are different, it breaks at different points, but it's also sort of L1 and then quadratic and then flat. There are other types of regularizers that people have also studied, but for which the theory is a little bit less clear, and that's something like L1/2. And the reason why these are not quite as good is because it turns out that if you look at something like the blue penalty, the L1/2 penalty, then it won't be true that all of the local optimum are well behaved. You'll end up with sort of a bad non-convex landscape. Okay, so people had kind of seen that this blue and the red, the green and the red penalties seem to give good behavior. I think I have a slide on this. So this is just a paper. Yeah, question.
What about weighted L1 if you can control the average coefficient?
Mm-hmm. Right. Yeah, so you could also look at some kind of weighted L1. There's also, what's it called? Log, can't remember. It came out of Candace's group, but there's some other log penalty of some sort, and they all have this sort of shape that as you get further away, they get flatter. Yeah. Yeah. Yeah, these are all non-convex. Everything except for the black one is non-convex. I don't remember off the top of my head what the weighted L1 penalty looks like. Yeah. But I'm guessing it probably is non-convex because then you want to have this shape so that you decrease the effect of the larger coefficient. Yeah. All right. So it's sort of known in the statistics literature that these sorts of regularizers seem to be good. And what I mean by seem to be good is that people knew they were non-convex. And so they said, well, I don't know if I can find a global optimum, but let me run some kind of gradient descent and find a local optimum. Let me run it again and again. And then it turns out that if you take the minimum over everything you've seen, then that solution is still very close to beta star. Okay, so there's this nice survey paper by Berhaney and Huang, which sort of just compares the lasso with the MCP and the SCAT. So this is like a mean squared error. Yeah.
Non-convex optimization listed that, but that's the problem.
Mm-hmm.
What you suggested right now. It's a good idea.
Yeah, so that was our contribution actually. So the theory that I'm about to present is to say that we know how to handle the green and the red and even the yellow one. We don't know how to handle the blue one. And in fact, you can prove or you can show that local optima are badly behaved for the blue one. Right. So I'm sort of trying to carve out what are the types of problems we can deal with and what's the type of theory or how do you get to the theoretical result. Okay, so this is just sort of saying what I've said already, that well, there's kind of this gap between local and global optima. And actually, there was some theory that, from statistics saying that the global optima of SCAD and MCP regularized least squares, were well behaved. And this is the sort of, a picture that we were able to show, that we were able to prove. So the picture is that our function is non-convex, and it might have a bunch of wiggles, but all the local optima are close. And one thing that I think is important to understand is that actually the global optimum beta hat might not be what we care about as statisticians. So as an optimization theorist, you definitely want to know what is beta hat. And you want to know how do the local optima compare with beta hat. But if you're thinking about it from a statistical perspective, then you just care about beta star. You want to estimate this underlying parameter vector that is generating your function in the first place. And so, well, some statistical theory will tell you that beta hat is pretty close to beta star. And how close is it? Well, it will depend on assumptions on x and y and the epsilons. It'll depend on the problem sizes. Of course, you can deal with high dimensions, p bigger than n, but if p is way, way bigger than n, you might be in trouble. So the type of theory for the lasso tells us that beta hat and beta star are within order of root k log p over n of each other. And what we were able to show is that any local optima of this problem are going to also be close to beta star within that radius. All right, so they're all equally close to beta star, and that's why we can choose any of them. Okay, so now I just want to give you some sense of the types of closeness that we measured, or that we quantified. So you can talk about the estimation error. So we quantified L1, L2, L infinity closeness. You can talk about the prediction error. So what is the value of your loss function, and is it converging to 0, and how quickly? And then of interest as well, which was somewhat harder to prove, was to show that the variable selection, show variable selection consistency as well. Yeah, question?
So I was to use the framework of errors and variable, it just the general framework of non-convex in the M-estimators.
Yeah, so I'm slowly going to unravel the generality to which these results hold. So they won't hold for any non-convex M-estimator, right? So we are able to come up with some conditions that will tell you if the loss satisfies this and the regularizer satisfies this, then the shape of the function is like that, right? And this, one special case would be errors in variables with SCAD penalty, for instance.
And also, so you said that using non-convection will improve prediction. Is it like in a high dimension setting or even low dimension setting?
I think both in high dimensions and low dimensions you should have less bias. Yeah.
So whenever you are mentioning consistency,
Uh-huh.
you mean just the existence of solution, or you mean?
Oh, it's not just existence. It's saying that this thing is actually converging to zero. So in statistics, consistency means that your estimator is converging to the actual thing. So we want to bound this by something that's going to zero. Right? And so the statement will be something like, well, if the data are coming from a Gaussian model or something like this, and if n is bigger than k times log p, then we have consistency, right? Because we want this error to be going to zero, so that tells us what the problem size of scaling is. Yeah. Okay. Right. So now I'm going to talk about this in more generality. So we have a loss function and we have a regularizer. And our theory requires that this regularizer be sort of separable. So it's like L1, you take an absolute value of every entry and you sum that up. And so we don't want to deal with cases when it might be not homogeneous, although you could try to extend the theory to that case. So if we have a SCAD penalty, some sort of shape like this, then we're again summing up that function applied to every coordinate. Another thing that we had to do was we added an extra constraint. And so the reason for adding some extra constraint, so now our regularization parameters are sort of like lambda and r. Okay, so lambda was telling us how to weigh off, to weigh between the loss and the penalty, and then we also have some constraint r, which is telling us just how far we want to go out. And we required this for our theory, just to say that, in fact, local and global optima will exist. Because if we have some directions in which we have negative curvature and things are going off to negative infinity, then, it might be vacuous to say, like, let's consider a local optimum. Okay. So now the conditions that we impose on the loss and the regularizer, well, so the loss function needs to satisfy something known as restricted strong convexity, which I will go into more detail about. And then the regularizer, there are a couple of more conditions that I'll list on the slide. But the most important ones are that at zero, the subgradient needs to be bounded, so we can't have an L1/2 penalty. And in fact, as I said, those cases will give you local optima that are far away. And then the other thing we need is that the regularizer can't be, so it needs to be that if we add some quadratic curvature, then it becomes convex. And actually, the reason for, well, one motivating reason for putting this as a condition was that we really wanted to deal with these SCAD and MCP regularizers, and the ones that look like L1 and they have quadratic curvature and they flatten out. So as long as mu is the maximum, or is the value at which we have negative curvature, then we will be able to convexify it. Okay. And then the result that we have is roughly that if this restricted strong convexity, which I haven't really explained yet, is bigger than the negative curvature, then we have this nice shape, right? And this curvature is connected to the design matrix. So the x's in the linear model will be generated from some distribution, and you can think about alpha as being a minimum eigenvalue of sigma x. Okay, so we want some curvature in the x's. Okay. And more formally, the statement is that the local optima, well, actually what we mean is all of the stationary points that satisfy this first order optimality condition will be close. So for the proper choice of the two regularization parameters, then the distance between beta tilde and beta star is going to be something like this square root k log p over n rate. Okay, so now I'm going to do my technical digression 1. So as I said, I was going to do some things on the board. So I figured that since this is sort of a short course or tutorial, I should talk about some of the very important ideas in this area of high-dimensional statistics. And then my goal will be to go through some argument and then to kind of tell you how it needs to be adapted in our particular setting. All right, so what I'm going to talk about is the theory for the lasso. So no non-convexity right now. So this is a nice convex program. So what we have is beta hat lasso, and this is arg min of 1 over 2n y minus x beta 2 norm squared plus lambda times L1 norm of beta. Okay? And the theorem is that, let's say, if the sparsity level of beta star is less than or equal to k, then under suitable conditions, on x and epsilon, we have beta hat minus beta star in 2 norm is less than or equal to c times lambda times square root of k for lambda sufficiently large. Or maybe I'll just write it like this, for lambda at least square root of log p over n. Okay, so this is the standard sort of lasso theory. Yeah. Okay, let me remind you. Y is equal to x beta star plus epsilon. All right, so you could say under suitable conditions on x and y, but we'll say x and epsilon. Okay, so I'm going to go through the argument for this, which I think is useful to know if you haven't seen it before. Okay, so, well, are we going to have a, should I keep going over here? Should I erase that? All right, let's do that. Okay. Oh, raise, not erase. Whoa. Oh, so this goes, and then this goes down? Ah, okay. All right. Raise. Okay. Okay, so the way that these arguments go is that you start with a basic inequality. This is what they call the basic inequality. Okay. So the basic inequality says, well, the one thing I do know about beta hat is that it's optimal. So the objective function evaluated at beta hat had better be less than or equal to the objective function evaluated at beta star. Okay, so what that means is 1 over 2n times y minus x beta hat 2 norm squared plus lambda beta hat 1 norm should be less than or equal to 1 over 2n y minus x beta star 2 norm squared plus beta star 1 norm. Okay, and then now you do some algebra, so rearrange. And I guess also substitute y equals x beta star plus epsilon, so you can get rid of the y's. Then what this will give you is 1 over n times x times beta hat minus beta star 2 norm squared is less than or equal to 2 epsilon transpose x beta hat minus beta star over n plus 2 lambda beta star 1 norm minus 2 lambda beta hat 1 norm. Okay, so this is plausible, right? You just plug in the value of y, and then you have x times beta hat minus beta stars coming out in some quadratic form. Okay, so what we want is we would really like to bound the left-hand side by beta hat minus beta star 2 norm squared times, let's say, some alpha. So lower bound. All right, so at the end of the day, we want some bound on the L2 norm of beta hat minus beta star. So it would be awfully nice if we could replace this by alpha times something. Okay. Unfortunately, we can't do that. And the reason that we can't do that is that, well, this is, the left-hand side is beta hat minus beta star transpose x over n, beta hat minus beta star. Right? And then we're in trouble because as we recall, this matrix is bad to work with. It has 0 eigenvalues. Okay, so that doesn't quite work. But what actually does work is instead we need to show that, or I should say first, show that beta hat minus beta star is in some cone set, which I will define momentarily. Okay, so the point is that beta hat minus beta star is not some arbitrary vector. It's actually a special vector. And the reason is that beta hat was solving the lasso. So beta hat is somewhat sparse. We don't know that off the bat that it is actually sparse because all we're doing is we're solving this, right? And it might not be supported on beta star. But beta star is sparse, and if beta hat is reasonably sparse in the direction of beta star, then this vector itself is going to be kind of low dimensional, right? So it might be kind of roughly k-dimensional if both of these were sparse in the k-dimensional set. And in that case, we would be fine, because we would be looking at a low-rank matrix, and we're just looking at a k-dimensional projection, and that's okay. So the first step is that we need to show that this is in some cone set. So how do we do that? Oh, I see. Okay. Oh, wow. It's like a conveyor belt. Okay. So define the cone set is equal to the set of all vectors in R to the P such that V sub S complement is less than or equal to 3 times V sub S. All right, and here S is equal to the support set of beta star, which is of cardinality less than or equal to K. All right. So it turns out, so what we're saying is that the amount of mass on the off support is going to be less than the amount of mass on support. So why do we call this a cone set? Well, as an example, in 1 dimension, or maybe 2 dimensions, if we looked at plotting S versus S complement, then I guess we would be looking at a line, and the things in the cone set would be here and here, right? And so this is actually a cone set, a subset of the plane. And furthermore, the sparse vectors, or the ones that are just supported on S, would be in here, right? So this cone set is kind of an enlargement of the set of vectors that are supported on the true set. Because of course, I mean, we can't expect that beta hat will be completely supported just on the support set. Okay. So we want to show that this is true. So maybe let me go through it because it's not actually that hard. So to show that beta hat minus beta star is in cone set, then what do we do? Okay, so we look at that inequality up at the very top. So the lower bound, the left-hand side of the topmost inequality by 0, right? So that's something we can do because that's obviously bigger than equal to 0. So then we get an inequality. So 0 is less than or equal to 2 epsilon transpose x beta hat minus beta star over n plus 2 lambda beta hat beta star 1 minus 2 lambda beta hat 1. Okay, so this is starting to look good because what we really want is something about beta hat minus beta star, so we need to use a triangle inequality and sort of separate out S and S complement. Okay, so now we'll use Holder's inequality because we want to just deal with L1 norms. So we have beta hat minus beta star L1 norm times 2 times the L1 norm of L infinity norm of x transpose epsilon over n. And then we have 2 lambda beta star 1 minus 2 lambda beta hat 1. Okay. Great. So now let's separate out the stuff that is on S and the stuff that's not on S. So we'll use the notation that nu hat is equal to beta hat minus beta star. And then what we have is that 0 is less than or equal to 2 x transpose epsilon over n infinity norm times the L1 norm of nu hat plus 2 lambda. And now I'm going to write this as nu hat S1 minus, or what do I want to write this as? Sorry. Let's do it slowly. So I have 2 lambda beta star S, 1 norm, plus 2 lambda beta star S complement, 1 norm, minus 2 lambda beta hat S, 1 norm, minus 2 lambda beta hat S complement, 1 norm. And I can get rid of this term because I know that beta star is actually just supported on S. Right. And so then I can write this as 2, or less than or equal to 2 times the L infinity norm times nu hat 1 norm, and I'll write plus 2 lambda nu hat S minus 2 lambda nu hat S complement. Okay, so here I have used the triangle inequality. All right. Yeah, so I use the triangle inequality to get this, and then I said here that nu hat S complement is just beta hat S complement. Okay, so that's a little bit of sleight of hand, but when you do this enough times, it's sort of the same procedure whenever you're dealing with penalized high-dimensional things. Okay, so we're almost there. So now what we do is we need to choose our regularization parameter appropriately. So if we could replace this by something like lambda, then we would be in good shape. Okay, so let's now assume that this is less than or equal to lambda times this guy plus 2 lambda nu hat S 1 norm minus 2 lambda nu hat S complement 1 norm. So now this is assuming that we choose lambda large enough. So assuming that lambda is at least 2 times x transpose epsilon over n infinity norm. Okay, so there's always this choice of the regularization parameter, and in particular, the regularization parameter needs to be big enough. And if you do that, then you rearrange everything, then this will imply that nu hat is in the cone set. Okay, because you have 1 lambda here, so that gives you a 3 lambda. You have another lambda here, so that gives me a negative lambda. I bring that over, and I get exactly what the cone set was. Okay. Okay, so we did all of this work to show that this thing is in the cone set. And now what does that mean? Well, then we need another assumption. So this is called the restricted eigenvalue assumption. And the restricted eigenvalue assumption is that for all vectors in the cone set, we in fact have V transpose x over n, V bigger than or equal to alpha times V 2 norm squared. Yeah, question? Mm-hmm. Mm-hmm. Say it holds with high probability. Right. So everything in this derivation so far is done deterministically. Right? You just have an x, and you have a beta, and you have an epsilon. And then we'll start to talk about with high probability. Okay, so even this restricted eigenvalue assumption, this you can think about as a deterministic thing. If someone gives you a design matrix X, then hopefully, or one can wishfully hope that it actually satisfies this inequality. The hard part, of course, is to say now if X is drawn from some kind of design, so if it's Gaussian, for instance, that this actually holds with high probability. And that does hold, so that's nice, but it takes extra work. Okay, so the assumption that people usually assume, so just to be clear, we've assumed 2 things so far. So the first thing we assumed was this thing, and now the second thing we're assuming is this thing, right? And those are the only two assumptions we need. Okay. So if this is true, then if we go back to that inequality we had up above, so then back to the earlier inequality. Then we can actually get alpha times the 2 norm squared is upper bounded by, well, maybe let me rewrite what the earlier inequality was. It was 1 over n times x nu hat 2 norm squared less than or equal to 2 epsilon transpose x beta hat minus beta star over n plus 2 lambda beta star 1 minus 2 lambda beta hat 1, right? So our earlier inequality was this part, and now we're saying let's just plug in this lower bound that we wanted. Okay, so now we just need to rearrange things to figure out what the right bound is on 2 norm. So this is just a deterministic condition. To show it holds with high probability, you need n to be bigger than k log p. All right. So basically, if n were really, really big, then this would converge to sigma x. So it would be great. It would hold for all vectors, right? So if n is sufficiently large and the x's come from a Gaussian ensemble, then this holds. Yeah. Question. Yeah. So we're assuming that epsilon is 0 mean throughout. Yeah. Otherwise, you could just take this constant and absorb it into your x. Yeah. Okay. Great. So we have this thing, and now we're just going to massage it a little bit more. So if we massage it a little bit more, then, well, so earlier we ended up with a bound like, I won't repeat the algebra here, basically 3 lambda times nu hat s 1 norm minus lambda times nu hat s complement 1 norm, right? So we used Holder's inequality, we assumed something about lambda, and we ended up with this bound, which is how, when we said this is bigger than or equal to 0, then that gave us the cone condition. Okay, so we recycle all of that, and instead we have this thing is upper bounded by this thing. And now we want to turn this thing into a 2 norm. So it'd be really nice if we could get some constant times a 2 norm, because here we have a 2 norm squared. And really what we're after is the 2 norm. So if we get something like a 2 norm, then we're in good shape. So how do we do that? Well, the nice thing is that, well, actually we can just eliminate the second term, right? So this is less than or equal to 3 lambda times S1 norm, and then now we can just use the fact that, well, if this is k sparse, then dimension k, so you can bound the L1 norm by root k times the 2 norm. So this is less than or equal to 3 lambda times root k times the 2 norm, okay, which is, of course, going to be bounded by the 2 norm of nu hat. Yeah, question? No, so we're assuming that beta star is k sparse, and that's all we need so far, right? So if we're going from here, well, up to here, there's no assumption of any sparsity, right? Here we're just going to eliminate the second term because it's negative, and then now we say this is just a restriction to k sparse. Yeah, great. Okay, so then we're basically done because now we just divide by the proper L2 norm. Okay, so therefore, the L2 norm is bounded by 3 lambda root k over alpha. Yeah, that's actually it, right? Great. And so this thing itself was just beta hat minus beta star, right? Okay. So now this still looks a little bit mysterious, right? So you're probably still wondering, like, what is n supposed to be and what is the design supposed to be? So if we now look at some distributional assumptions, so the question is basically, how big should lambda be? And when is the restricted eigenvalue condition satisfied? Right. So the restricted eigenvalue condition, this requires some conditions on X. Right? Because it was something about the minimum eigenvalues of the X matrix. And then how big lambda should be? Well, we assume that lambda is at least 2 times x transpose epsilon over n. Right? So now let me just make some statements. So the first fact is that if the x's are drawn from some Gaussian distribution and their IID, then the RE condition holds with high probability if n is at least k times log p. Okay? And I should say that the RE condition holds with alpha equal to something like the minimum eigenvalue of sigma x and maybe divided by 2. Okay? So at the population level, the minimum eigenvalue should just be alpha, but you lose a little bit because you need to talk about concentration of things, because you're really talking about x transpose x over n and how quickly it converges to sigma x. Okay, so it's a nice result of Rascuti et al. That this actually holds with high probability for the Gaussian case. All right. The other question is about the lambda, and this is where you see that it tells you something about how big the sample size has to be. So it needs to scale linearly with the sparsity, and it needs to scale logarithmically with the dimension. So that's good because, I mean, if it weren't sparse, then you would think that you need something like n bigger than or equal to p. If it were sparse and you knew exactly which coordinates to focus in on, and you just did a linear regression on those k-dimensional things, you need n to be at least k. And here this is saying that if you don't actually know where it's supported, but you do know that it's sparse, and you run a lasso, then you can get away with a sample size that's scaling linearly with the actual sparsity and then logarithmically with the ambient dimension. Okay. But now we want to know how big should lambda be. And the reason we want to know how big should lambda be is that our bound here says that it's something that scales with lambda. And so you would expect that if lambda is too small, then you're not actually enforcing sparsity, so your beta hat is going to be far away. Right? If your lambda gets really, really big, then you're sort of squashing everything down to 0, so your error should get bigger and bigger. So sort of the sweet spot of lambda is when lambda is equal to whatever this infinity norm thing should be. Right? Okay, so the other fact is that if, let's say, the epsilon i's are normally distributed with mean 0 and variance sigma epsilon squared, then with high probability, the term x transpose epsilon over n infinity norm is less than or equal to some constant times square root log p over n. Okay, and so this is something